Okay, so I really wanted to show you guys that simulation. I think using this simulation will really help you understand how Vesper is working. Here's a central atom with two things connected. You can set how many more atoms you want with either a single bond, a double bond, or a triple bond. You can stick a lone pair in there. You can do that by just clicking on it, or you take it away by hitting the X. And here you can see, here's a central atom with two things connected. You can set how many more atoms you want with either a single bond, a double bond, or a triple bond. You can stick a lone pair in there. You can do that by just clicking on it, or you take it away by hitting the X. You select these, you can show what the base geometries are. So linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral, those will show up, as well as the molecular geometries that we've been discussing. So here, let me do carbon dioxide. That's got two double bonds, and that's it. That's the one that we've been working with for linear. It gives you a linear shape. And you can see what's happening with Vesper. If I try to drag one of these atoms closer to the other, right, the repulsion in these double bonds, it's going to push the other ones away. So that no matter what I do here, it's going to force it in a linear configuration. Now, because there's no lone pairs on here, the steric number around the central atom is going to be Sn of 2. There's the one package, there's the other one. So that gives you the electron geometry is linear and the molecular geometry is linear. Now let's go back to just putting single bonds in here now. If I add a third one, right, the electron geometry is trigonal planar. That's the base geometry. And remember that if there's no lone pairs, the molecular geometry is the same as the base geometry. But now look at what happens when I try to move one of them relative to the others. Because of the repulsion of the electron pairs, Vesper, all right, they are going to arrange themselves in a trigonal plane. Here's the plane. See, 3 points in space define a plane. So if I try to take one of these out of the plane, it's going to push the other two away, so you're always making a plane. Now, if I added a lone pair to that, the steric number goes from 3 to 4. The lone pair, here, let me put this back in a plane. Look what happens when I add a lone pair. It pushes them out of the plane and into a pyramid with a trigonal base. So that's the difference between an Sn of 3, and there's no lone pairs, so it's trigonal planar, and an Sn of 4 with one lone pair, and it's now trigonal pyramidal. But the electron geometry is tetrahedral. And we can see that if we put all 4 bonds there with the atoms, now we can see there's your tetrahedron. Right? If we added another one, now we have an Sn of 5. The Sn of 5, that's the tricky one. That's the one that's got the 2 different sets of bond angles, because you have the 3 atoms that arrange themselves in a plane. That's the trigonal plane there in the middle, see? And then you have 2 additional atoms that are axial to that plane. Wherever that plane is, the other 2 are axial. This is how it naturally distributes when you have 5 packages of negative charge that are all repulsing from each other. If I try to move any of these around, the other ones are going to redistribute back into this trigonal bipyramidal shape. See, now the plane is here. And if you want to do that with double bonds, if you want to see what the relative strengths are, again, you know, single, double, triple, this mode is set to just show you the base geometries, and then the geometries that result when you now replace these with lone pairs. So here, I think I went to octahedral now. So here's octahedral. Let's go back to trigonal bipyramidal. Now, I told you that when you put a lone pair in, the lone pair is going to occupy the position that gives it the most room to breathe. That's going to be one of these 3 equatorial positions. So if I pop a lone pair in here and take away one of the shared pairs, so now I'm back to my trigonal bipyramidal electron geometry. And look at the molecular geometry. It's the seesaw shape. There's your seesaw. But that lone pair went into one of those 3 equatorial positions. You can see there's the plane. There's the equatorial plane. And these are the 2 that are axial to it. If I pop in a second lone pair, right? We're back to trigonal bipyramidal. And now both of them are in the equatorial position. And this gives us the T shape. If I plug in a third one, now all three of them are in the equatorial plane. That leaves the other two bonded atoms in the axial positions. That gives it a linear configuration. Okay? And you can test all that by, again, moving these things around and seeing how Vesper works to redistribute that. If we go back to we only go up to 6. That's really all we find in nature. And this simulation won't go beyond an SN of 6. But with an SN of 6, now the electron geometry is octahedral. That's your base geometry. And no matter what you do with any of these, it's going to force all the other ones into this octahedral configuration. And in that, you will always have 4 that are in a plane, and the other 2 are axial to that plane. Now, that plane can be any of these 4. See, as I rotate this around, no matter how you rotate it, you can always find 4 in a plane and 2 that are axial on opposite sides of that plane. So when you stick a lone pair in here, that first lone pair can go anywhere. It doesn't matter. But when you put the second one in, the second one will always go on. See, do you see what happened there? Here, let me go back. So here's one lone pair. Look what happens. I think the algorithm actually sticks a lone pair in one place, and then it shows you how it moves naturally to, let's see if I can do that again. Well, I didn't this time, but it naturally will position itself opposite, right? This is the way that you can get 2 lone pairs in the most stable configuration when your electron geometry is octahedral, when the steric number is 6. Okay, so play around with that if you want, if it helps you visualize things. I think it's a really useful tool, and now you know where it is. Okay, so why do we care? Why does it matter that we can tell the geometry of these molecules? As you may or may not learn in your future classes, depending on what your major is, it makes a big deal what the shapes of these molecules are. Sometimes if you're going into biology or molecular biology or biochemistry, the shapes of certain molecules, let's say that they're enzymes and substrates, and how substrates fit into the active site, or how certain inhibitors might block enzyme activity. Shape has a lot to do with how these larger macromolecules fit together. Or sometimes if it's like in a square plane, nice square plane, that fits real nicely between the base pairs of your DNA and can cause mutations, right? So a lot of drug discovery, for example, is involved in making molecules of a certain shape that might inhibit an enzyme that gives you high cholesterol and lowers your cholesterol, or making mutations and design molecules in that sense. We can also make a lot of predictions on the physical and chemical behavior of molecules based on their shape. And in fact, chapter 6 in our textbook goes into a lot of this. Chapter 6 is on intermolecular attractive forces. Inter means between molecules. We've been talking about intramolecular interactions. Those are the covalent and ionic bonds. But later on, you're going to be learning, well, if you take Gen Chem 2, we're not actually going to do chapter 6. We're skipping chapter 6 after this and going into chapter 7 next. But for those of you who are continuing on to Gen Chem 2, I'm going to give you a taste of that now, because one of them is the interaction between polar molecules. This whole business about dipole moments that we've been talking about. So we're going to have a discussion now on polar versus nonpolar. This can have an impact on the physical and chemical properties of molecules. In particular, what we're going to look at today is boiling point and melting point. We can think of those as the same thing. Of course, they're talking about two different phase transitions. So boiling point and melting point. I think most of you can probably identify or tell me what the boiling point is. What's happening at the boiling point? In simple terms, it's going from a liquid to a gas, all right? There's actually a much more complicated definition of it, but we're going to go with this. Going from the liquid phase to the gas phase. And what's happening at the melting point? It's going from a solid to a liquid. Very good. And if you recall from chapter 1, if we went in reverse, all right, going from a gas to a liquid, we would call that the condensation point. And if we were going from a liquid to a solid, that would be the freezing point. They're the same thing. It just depends on which direction you're going, okay? But what those values are absolutely influenced by the polarity of the molecules, whether something's polar or non-polar. Because when it's polar, what do you have when you're polar? You have opposite charges. You have one of these things. Remember these things? What's that called? A dipole moment. Dipole moments have two poles. They have one that's slightly negative, and they have one that's slightly positive. These are vector quantities. And for those of you math aficionados out there, vector quantities have magnitude and direction. And we can actually measure the magnitude of dipole moments. Don't worry, we're not going to in this class, but we can talk about it in relativistic terms. Qualitatively, we can talk about what happens to the magnitude and the directions of these dipole moments. Now, we've been talking about dipole moments with respect to the bonds. Remember, we have polar covalent bonds and non-polar covalent bonds. And you may recall from chapter 4 that the only molecules that really have non-polar bonds, there's only about 7 of them that I told you about. Remember what they are? G, E, N, and I, N, E are found in nature diatomically, which means diatomic molecules, they have the same atom on both sides of the bond. That means the electronegativity of those two atoms is exactly the same. So what is electronegativity? You got to remember all this stuff, right? This dipole moment happens due to a difference in electronegativity, delta En. Remember that? If there's a difference in electronegativity, the electronegativity is the general attraction that an atom has for those electrons that are shared in a covalent bond. If you have the same atom type on both sides of the bond, it's the same electronegativity, so those electrons are equally shared. But in something like carbon dioxide here, right, if I were to just generally draw a carbon-oxygen bond like this, not specifying whether it's a single bond or a double bond or whatever, there's a difference in electronegativity here. The oxygen is more electronegative than the carbon, so it's going to have a stronger attraction for those shared electrons than the carbon will. That's going to create a skewed distribution of the electrons. So they're not equally shared. You're going to have more electrons closer to the oxygens than you are to the carbon. So you're going to have the dipole moments. They're drawn there in red for you. The arrow head always points to the delta negative. Okay, and the plus sign on the tail is always the delta positive. So those are polar bonds. They're both polar bonds. But now you play in Vesper. Okay, what's the steric number of the carbon in carbon dioxide? It's a 2. So what's your base geometry when the steric number is 2? It's linear, and we don't have any lone pairs on here. So this molecule is linear. And what do you know about a linear molecule? The bond angles. It's 180 degrees, right? Which means they're in opposition. So even though these bonds are polar bonds, because of the difference in electronegativity, they are going in opposite directions. It doesn't matter whether the arrowheads are pointing out or pointing in. All that matters is that the dipole moment is exactly the same. They're both carbon oxygen, in this case, double bonds. So whatever the magnitude is, we don't care numerically, right? But whatever it is, it's the same magnitude for both of these bonds. And these bonds are in a linear configuration, so they are in opposition. So they will completely cancel each other out. So overall, this is a neutral molecule. There is no overall dipole moment in this molecule because the dipoles of the bonds cancel out. Does that make sense? This overall is a non-polar molecule. The dipoles cancel out. Here's another example. Here's carbon tetrafluoride. Now, I don't have all the lone pairs drawn in here because I want you to focus on the dipole moments. Each one of these carbon fluorine bonds has a dipole moment. They are polar covalent bonds. But I'm just showing you the dipole moment. I'm not putting a number on here because all four of them are exactly the same bond. All four are carbon fluorine bonds. So whatever the magnitude is, it's the same, okay? But now you look, this is an SN of what? What's the SN on the carbon? 4. So what's your base geometry when your SN is 4? Tetrahedral. Are there any lone pairs? No. So what's the molecular geometry? Tetrahedral. All right. So tetrahedral, it's a base geometry. When you have the vertices of a regular polyhedron, the base geometries are all regular tetrahedrons. Think of them that way. When you have the base geometry, the bonds will always be the vector part, the direction of these bonds are always going to be in opposition. It's harder to see in a tetrahedron. It's easy to see in linear, okay? But the base geometries, let's just put this in writing here. All base geometries have the bonds in opposition. Meaning that their dipoles will cancel. Now that's dipoles of equal magnitude, and that's all I'm showing you. Here, it's so important, I'm going to highlight this in red. I'm also going to lower it a little bit so I can show you something in a little bit with water here. Okay? So tetrahedral is a base geometry. Here's a way that maybe will help you think about this a little bit better. Imagine that the carbon in the center here is a ball, okay? And instead of having fluorines connected by covalent bonds, let's attach a horse with a rope to a ball, okay? And all 4 horses are the same type, so they all will have the same strength in speed and whatever, and force that they would carry with them, all right? So they all start out wherever, doesn't matter, all right? But they're all attached by a rope to the central ball, all right? And then you go, whoosh, all right? And all 4 horses start going as fast as they can. And then, of course, the rope's going to get tight, and they're all going to be pulling against this ball. But they're all running as fast as they can. So they will end up, if they were running in 3-dimensional space, going as far away from each other as possible, given that though they're stuck, they're tethered, if you know what that word means, they're stuck with the rope to this central ball, they're going to all end up running away from each other along the 4 vertices of a tetrahedron. And in doing so, they're running away with the same strength Is that ball in the center going to move? No, because they're all running in the opposite directions. In this case, in three-dimensional space, 4 of them in opposite directions gives you the vertices of a tetrahedron. If we did it with 5 horses, they would end up running out along the vertices of the bonds in a trigonal bipyramid. And if there were 6 of them, it would be octahedral. Okay, so maybe that's a different way to help you visualize it. The point here is that if you've got the geometry of one of those base geometries that I showed you at the beginning of this chapter for your steric numbers, there's your base geometries, the 5. All right, if you've got that and the dipole of the bonds are all the same type, same magnitude, they will cancel. Plain and simple. If you've got a lone pair though in here, you're not going to have the base geometry for the molecular geometry anymore. All right, and they're not going to cancel anymore. Now, it's not a steadfast rule, but for most cases, if you've got a lone pair on there, it's going to mess things up and they won't completely cancel out. Let me show you an easy example of that. That's with water here. So here's water. What's the steric number on that oxygen? It's 4. The steric number, 1, 2, 3, 4. It's the packets of negative charge. But we've got 2 of them are in lone pairs. So the oxygen-hydrogen bond, that is a polar covalent bond. Consider all of them as polar covalent bonds unless it's a diatomic molecule where the atom is the same on both sides. All right, so it's the same magnitude. Same magnitude of the dipole moment between the hydrogen and the oxygen. But what's the shape? What's the molecular shape? What's the molecular geometry, I should say? It's bent. It's not linear because we started with tetrahedral and then we added 1 lone pair, which would have given us trigonal pyramid or pyramidal. And then we added a 2nd lone pair that gives us the bent shape. And in the bent shape, notice that even though it's the same magnitude, they're no longer in opposition. So this is the same magnitude, but they're not opposite anymore. So the dipoles don't cancel out. And so what you end up with is overall across the entire molecule, you have a dipole moment. Let's do it with my highlighter here. There's an overall dipole moment here. It's what we call a permanent dipole. The way this works, sorry, permanent dipole moment across the molecule here. So overall, water is polar. Water has a slight negative side and a slight positive side. Not the bonds anymore, okay? So I'm going to put a delta positive side over here. And I'll put a delta negative side by the oxygens, whoops. And you would expect the delta negative to be by the oxygens. I wouldn't hold you to knowing that, but I think it's pretty obvious. The oxygens are most electronegative. They're going to be attracting most of the electrons, most of the shared electrons here. So the negative side of the dipole is going to be oriented towards the oxygen, and the positive side, what's left over, is going to be oriented where the hydrogens are. But overall, water is polar because even though the magnitude is the same, the directions are no longer opposite. For it to be nonpolar, it has to be both the same magnitude and in opposition. Anything other than that, and it's going to be polar. So let's add that little statement, right? Nonpolar is going to be anything that's equal and opposite dipoles. Now, that's dipoles in the bonds, bond dipoles. If it's not equal, but they're in opposition, it's still going to be polar because now the magnitudes aren't the same. And I'll show you an example of that. Okay? If they're all equal, but they're not in opposition, they're not going to cancel out and it's going to be polar. All right, so we've got SO2 and CO2, sulfur dioxide and carbon dioxide. They look about the same, right? They 3 atoms each. If we were to count the molar mass, count up the molar mass for them, sulfur, and let's just do this rounding with some creative rounding. So sulfur is about 32, and each oxygen is about 16. So overall, nice round number. This is about 64 atomic mass units, right? 2 oxygens is 16 plus 12 for the carbon. That gives us 32, 44. So they're relatively close in mass. They're relatively close in what their overall shape. Okay. Let's take a look at their Lewis structures. We don't need to go from the start on the Lewis structures. You've seen plenty of these. You certainly should know what carbon dioxide looks like by now. Here's the Lewis structure for carbon dioxide. You may recall the Lewis structure for sulfur dioxide. We did that several times in lecture. That was your first example of hypervalency. Sulfur dioxide looks like this. What's the steric number on the carbon? Let's do a show of hands. All right. It's going to be 1, 2, 3, or 4. All right. Yes, it's 2. 1, 2. What's the steric number on the sulfur? Show of hands. Good. It's 3. What's the molecular shape? Now that one I can't do a show of hands on. What's the molecular shape of carbon dioxide? We already know that one. We just did it. It's linear. Okay. What's the molecular shape of sulfur dioxide? Is it linear? It's bent. All right. I drew it linear to make a point. The Lewis structure doesn't have to show the geometry. Okay. But you know it's SN of 3 and it's got 1 lone pair. So this is bent. Now let's look at the dipoles. The dipoles in carbon dioxide, as we just described, they're the same magnitude. So it doesn't matter what that magnitude is, they're the same. And as I showed us the previous example, they are in opposition. So here the dipoles cancel. Which means that they're equal and opposite. And what did I just tell you about equal and opposite? It's non-polar. Now, with sulfur dioxide, here I'm going to use a different arrowhead, just because the magnitude of an SO bond, double bond, is going to be different than the magnitude of a CO double bond, okay? But if we're just looking at sulfur dioxide, whatever that magnitude is, it's the same. All right, so we've got equal magnitude. But are they in opposition in the bent configuration? No. So they're not opposite. Which means that they are polar. It's a polar molecule. Meaning that the molecule itself has a dipole moment on it. This is a nonpolar molecule, so it has no dipole moment. So why does that matter? Okay, what do you get with the dipole moment across your molecule? Sulfur dioxide, if I now just, here, let's just put a bunch of sulfur dioxides up here. And let's put a bunch of carbon dioxides over here. I'm just saving myself a little bit of time not putting the double bonds in. Whoops, that's a carbon, okay? The carbon dioxide has no overall dipole moment. It has no permanent dipole. So there's no attraction. There's no strong attraction between the molecules of carbon dioxide. Sulfur dioxide, they all have a permanent dipole. Let's draw it this way with the negative going towards the oxygens. Doesn't matter if you know that the negative is towards the oxygens or not. What matters is that sulfur dioxide has a permanent dipole on it, which means if I were to zoom in on this, each one of them has a delta positive end and a delta negative end. Delta positive, delta negative. And when you have negatives and positives next to each other, what do? They attract, okay? So you've got an attraction here. That's an attractive force between the molecules, okay? Right, that's the intermolecular attractive force. So if we want to take sulfur dioxide and figure out what its boiling point is, for example, that's going to be the energy necessary to get those molecules separated from each other so that they go from the liquid phase to the gas phase. Same is going to be true if we were to define what the boiling point is for carbon dioxide. But look, carbon dioxide doesn't have any extra attraction between the molecules. So what do you think? Is it going to take more energy or less energy to get sulfur dioxide into the gas phase? Who thinks it's more? Who thinks it's less? Right, it's going to be more because there's an attractive force. There's an extra attractive force that you need to overcome to get sulfur dioxide into the gas phase. So let's take a look. Actually, what are those numbers? The boiling point for carbon dioxide is negative 78 degrees Celsius. And for sulfur dioxide, it's negative 10 degrees Celsius. Okay, so it takes more energy to overcome the attraction. But you can predict that now because you know all this stuff. So if I just gave you sulfur dioxide and carbon dioxide on an exam and asked you which one's going to have the higher boiling point, of course you won't just memorize the slide. You'll understand the process. You need to figure out which molecule is polar and which molecule is nonpolar. The one that's polar, that's going to have more attractive forces between the molecules, meaning that you can predict now that it will have the higher boiling point because it takes more energy to get those molecules to separate and escape into the gas phase. Here, let's do it with this example. Here's silicon tetrafluoride and sulfur tetrafluoride. Think about it for a minute, right? Work at it. Can you tell just from looking at those two, which one's polar and which one's nonpolar? Maybe you can, maybe you can't. What are you going to have to do if you can't tell from looking at it? Build the Lewis structure. You know how to do that. You know how to build a Lewis structure, and now you know how to interpret the Lewis structure. Okay? So when we build the Lewis structure, silicon, find it on the periodic table, right? Group 4, sulfur is in group 6. So there's going to be a little difference in the number of valence electrons that we have. But the fluorines are all the same. Okay? So this is going to have 4 plus 28. This is going to have 6 plus 28 electrons. Right? So 4 plus 28, so this is 32 electrons. This one's going to have 34 electrons. They're both going to be spokes on a wheel. In each one, the 4 bonds, that's 8 electrons. So I'm just going to fill in the rest. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We're done. So this one's going to be the same, except we've got two more electrons. Where are they going to go? They're going to go in the center. Steric number on the silicon is 4. Steric number on the sulfur is 5. So what do we have with silicon tetrafluoride? Is it going to be polar or nonpolar? What's the shape? What's the molecular shape? This is tetrahedral. All 4 bonds are the same. This is equal and opposite. So this is going to be a non-polar molecule. What's the molecular shape for sulfur tetrafluoride? It's the molecular shape is seesaw. The electronic shape is trigonal bipyramidal. But we have trigonal bipyramidal with one lone pair. That's going to give us seesaw. Seesaw is not in opposition. I mean, you've got a lone pair in there. It's not going to be in opposition. So these are equal, but they're not opposite. So this is going to be polar. Molecule. So which one's going to have the higher boiling point? Sulfur or silicon? The sulfur tetrafluoride. Sulfur tetrafluoride has a boiling point of positive 40 degrees Celsius, and silicon tetrafluoride has a boiling point of negative 90 degrees Celsius. Okay, so you can make those strong predictions. In most cases, if there's a lone pair, it's not going to be opposite. There are a few exceptions to that. In this case here, look at xenon difluoride. Because those 3 lone pairs are all in the equatorial plane, and the 2 fluorines that are left over, they're axial, this is linear. So what do you think? Is xenon difluoride, is that going to be polar or nonpolar? It's nonpolar, because these actually are in opposition. Here's another one, xenon tetrafluoride. Because of the 2 lone pairs here, it forces the remaining 4 bonds to be all in a square plane. That's actually going to cancel out as well. So there are a few exceptions, but beyond those exceptions, if you've got lone pairs in your molecule, it's almost always going to be a polar molecule. But so here, let me give you another challenge here. Let's look at this one. I'll save you some time and I'll actually give you the 2 Lewis structures. So here's exhibit 1 and here's exhibit 2. Which one will have the highest boiling point? 1 or 2? Show of hands. Almost all of you who raised your hand, who committed to an answer, chose number 2. But half of you didn't choose anything. Here, let me give you a third option. All right. What do you think? You still think it's 2? Or do you think they're both the same? These are in fact the same molecule. 1 and 2 are exactly the same. They will have the exact same boiling point because it's not a cross. See, I fooled you. All right, it's not a cross, it's a tetrahedron. All right. If I fool you once, it's on me. If I fool you twice, it's on you. Okay, so don't get fooled by this again. The Lewis structure does not have to show you the actual geometry. And we always draw these as crosses because it's a lot easier to do that than to try to draw it in 3-dimensional shape, which would be something like this with the wedges. And let's not worry about drawing them that way, okay? You have to remember how to interpret these things. The tetrahedron, all right? They're all equal. So this chlorine here is no closer or farther away from this atom than it is from any of the others. They are all equally distant from each other because they're in the regular vertices of a tetrahedron. Okay, so these are in fact both the same. Let me give you one more challenge. Let's see what you make of this. Let me give you BH3, SO2, CO2, and CF4. Which one's going to have the higher boiling point? And we'll do a show of hands. Think about it for a minute. 1, 2, 3, and 4. And if you can't tell, jot down what the Lewis structures are. All right, let's see, show of hands. What do you think? 1, 2, 3, or 4? Which one has the higher boiling point? It seems that most of you are picking 2. 2 is the right answer. What you're looking for is what property can you deduce from this going to the Lewis structure to the geometries and what you know about Vesper theory and how that's going to affect the polar bonds. Are they going to be equal and are they going to be in opposition? This is the only one that's polar. All of the rest of these are nonpolar. You already know that carbon dioxide is nonpolar. Carbon tetrafluoride, you got to draw it out. But when you draw the Lewis structure, it's going to be this, which is a cross as we draw it, but we know it's not a cross. It's a tetrahedron, folks. So for all of you who guessed 4, I guess I fooled you twice after all. It's tetrahedral, which means that they're in opposition. If it's a base geometry of those steric numbers that we had on the first slide, they will be in opposition. So this is nonpolar. These are all nonpolar. If you did boron trihydride, this is an example of an incomplete octet. Right? It would look like this. Steric number is 3. No lone pairs. That's your base geometry. Trigonal planar. They are in opposition.